Thank you. Good job.
How's that?
Yeah, that's, well, yeah, I've got a booming voice, so yeah, okay. Excellent. So, thank you. What was it, by the way? So, one cable, okay. So, two protons are walking along one day when they bump into two electrons. Hey, say the electrons, let's hang out this Sunday. Sorry, reply the protons, we can't. Why not? Question the electrons. Well, the protons say, we've got mass. It's a little bit funny. Of course, the electrons have mass too, but not quite as much mass, you know. Anyway, there's a bunch here, but given the delays, I'll save them for another day. How do astronomers play football? They gather in Hubble formation, make a plan, and then go long. You know, Hubble sees far. Okay, yeah. All right, keep them coming, and I've got a few things I wanted to say before. Oh shoot, well it's 3:10, but I'll cover them anyway. This is a fun lecture today, and I wanted to do this before lecture, but I'll do it now because so many people asked me about it. I talked about the setting sun, and the rising sun does the same thing. Can't really tell, right, whether it's setting or rising, unless you know whether you're looking west or east. But anyway, the setting or rising sun has these shades of yellow, orange, and red, all right, because of these atmospheric effects. Some people ask me after class, does the moon do the same thing? And absolutely. The moon reflects sunlight way out there. You know, the atmosphere has nothing to do with that. But then the reflected sunlight from the moon goes through the atmosphere and gets selectively scattered and absorbed, just as the sun does. So some of you will have seen a yellow or an orange or even a red rising moon. Okay, how many of you have seen this effect with the moonrise? Yeah, okay. It's exactly the same thing as the rising or setting sun. It looks yellow, orange, or red for the same reason. However, the other effect that's interesting that many of you, all of you I'm sure have noticed about the rising or setting moon, especially when it's full, is what? It looks big. It looks gargantuan, right? I mean, you know, you look at that. It's just, every time I look at the rising moon, it looks gargantuan. Is it really bigger on the horizon than later that same night when it's high up in the sky? What do you think? No, it's not. It's not bigger. I know it's not. I swear, though, when I look at the moon, it is. And I even know what's going on, but it really does look big. And it's an illusion. People don't completely understand it yet. We think it has something to do with the fact that when objects are near the horizon, there are familiar other objects with which to compare them, like buildings and trees and stuff. And you do this comparison mentally even when there don't happen to be any trees or buildings or people on the horizon. You're used to looking at the horizon with trees and buildings and mountains. So things look bigger in proportion, although it's not universally acknowledged that that's the entire cause of the effect. You may question whether the moon really is the same size on the horizon as it is later that night. And I swear to you, it's in fact smaller when it's on the horizon than when it's high up in the sky. It's smaller when it's on the horizon because it's farther away from you by about 1 Earth radius, as you can see from this diagram, which is not in your notebooks, and this is just an aside that I was going to do in the few minutes before class. But here you are observing the moon, say, at midnight when it's high in the sky. See, it's overhead. Here's the overhead point. The horizon is when you're looking sort of tangent to the Earth's surface. So when you're looking at the moon, say, at midnight, you're this far away from it. When you're looking at the moon, you know, at sunrise or sunset, let's say, you're basically 1 Earth radius farther from the moon. So if anything, the moon is smaller in angular size when it's on the horizon than when it's high up in the sky. But I swear it doesn't look that way. I mean, I totally agree with everyone, but you can make measurements. You can take photographs of the moon the same night on the horizon and high up in the sky, and if you measure the imprint of the moon on your negatives or on your CCD digital camera, it's a small effect. It's 1 Earth radius out of 60, so it's only a 2% effect. But if anything, the moon is smaller on the horizon than on the when it's high up. And it's not entirely understood, but I think it's has something to do with this business of comparing things. Don't believe everything you see. Basically, there are many well-known optical illusions, including this one. But here's a cool one that I really like. Those lines, those horizontal lines are not curved. They're perfectly straight, it turns out. But how many of you, just glancing at this thing without analyzing it, would bet that the lines are horizontal and not curved, rather than tilted and possibly even curved? Right? I mean, I think everyone, if they're honest, when Brett says yes, everyone, if they're honest, would say that those do not look like horizontal parallel lines, but they are. If you take a straight edge and you measure those things, they are. Here's another well-known illusion. Which central circle looks bigger, the one on the left or the one on the right? The one on the left looks bigger. They're the same size if you measure them. So when you compare things with other things, your brain and your eyes can definitely play tricks on you. And the moon illusion is just that. It's some sort of a psychological effect when we're looking at the moon or the sun when it's near the horizon. But you're not as used to looking at the sun when it's high in the sky because it's so bright, so you don't usually compare the setting sun with how it looks when it's high in the sky. But a lot of people have looked at the moon when it's high in the sky, and it looks pretty small. And then you look at the moon when it's rising near the horizon, and it looks gargantuan. Don't believe everything you see. Okay, a couple of things. Quiz next week. I think everyone is aware of that. Homework 2 is due today by 5:15. By the way, you don't have to be there at 5:15. You're welcome to turn it in earlier in the day or earlier in the week. We don't want everyone there at 5:15. Just no later than 5:15. Okay. Some people email me, what if I can't be there at 5:15? I have soccer practice or something like that. Well, turn it in earlier, folks, okay? So, all right, thanks. Lick thing, if you're interested, give me something by 5 p.m. on Monday. Don't put it in the homework boxes, and go Bears. Anyway, I wanted to say a few more things about lunar phases before I go into one of my favorite topics in the universe, total solar eclipses. This is a fun lecture. But anyway, I talked about the lunar phases last Wednesday, and I wanted to just do a few more little things with them. First of all, to remind you what they look like and what they're caused by. They're caused by the changing relative orientation between the moon, which orbits the Earth, and the direction to the sun. So like right around here, let me pause it, all right? You don't see, well, you see part of, but not all of the sunlit side of the moon. You see just the part that's facing you, and that looks like this waning crescent here. All right, so those are the phases of the moon, and you can look at these little applets, and we're going to try to put them on VSpace for you. But I like also doing little demos. You should, I think, have gotten used to this now, where I like to do things with just plain old everyday devices that help you understand things. And this is something you can do at home. You don't need a fancy equipment, but put yourself in a darkened room. And it's easiest to do this if you do it with someone, and it's more fun as well. But you're the Earth, your eyes are the Earth, and this golf ball is the moon. And then in a dark room, have someone shine a light on the moon. And this is the sun, and put it pretty far away. I can stretch it out like this, this room isn't darkened, but that's okay. I just want to give you the idea. You don't have to turn off the lights, Alberto or others, but just do this at home. But you can see that when the moon is between you and the sun, you don't see the illuminated face, and so it looks dark. And when it's sort of a quarter of its orbit around, the illuminated face, well, it's the face facing this way, and that's why you shouldn't put the flashlight too close, because then it doesn't simulate a very distant sun. The sun is really far away on this scale, okay? So the light rays are coming in parallel from the right. So have a friend with a really bright light do this with you. And you can see that the half that I see is only half illuminated, and so that gives you a quarter moon. Then you put it a little bit further away, and you get a gibbous moon and then a full moon, unless my head blocks the moon. And what do you get in that case? A lunar eclipse. We'll talk about that either at the end of today or the beginning of Monday. And then you get the other phases on the other side. But of course, you can break your neck, or at least get a crick in your neck if you do this too much. So I will not pay for your chiropractor or doctor appointment if you do something terrible to your neck. So watch out. But this half of the orbit is pretty easy. So I like doing those kinds of things with just regular everyday devices. But we'll try to put these applets on VSpace for you. Okay, so that's that. The other thing I wanted to say is that there's a very strong relationship between the phase of the moon and at what times of the day or night you can or cannot see it. There are certain situations that are impossible. And I illustrate this here. The Earth is rotating about its axis in 24 hours, and that's what causes our apparent day. It looks like the sun orbits us in 24 hours, but that's not really what's happening. We're rotating about our axis. So at noon, we're standing somewhere here, and let's suppose we're at the equator, so you don't have to worry about weird effects near the poles and stuff. But here you are at noon, and you're looking at the sun, and it's overhead. And at sunset, why is this sunset? Well, because you're rotating, the Earth is rotating in, and at 6 p.m., roughly speaking, on the equator, at the equinoxes or whatever, well, on the equinoxes, even if you're not at the equator. But anyway, you're going from the sunlit side to the dark side. Not the dark side as in Darth Vader, but, the dark side of the Earth. And in particular, the sun is along a direction which is tangent to the surface here. That's the direction of the horizon. Okay, so the sun is setting there, and it's 6 p.m. So for example, if you're over here and it's 9 p.m., or let's say it's midnight. You can see the full moon if it happens to be full that night, right? Because that's just straight overhead. But could you see the waxing crescent at midnight? No. Why not? It's obvious. Just your gut feeling. That's right. The Earth is blocking your line of sight, right? You have to look through a tube drilled through the Earth to see the waxing crescent. So you cannot see the waxing crescent moon at midnight. At 6 p.m., can you see the third quarter moon? No. You'd have to look straight through the Earth. Okay, here's a good one. What time of the day, roughly speaking, does the full moon rise? What do you think? Time of the day or in relation to the sun? Again, you put the moon far away, so imagine it quite far away compared to the radius of the Earth. This is the direction of the full moon. When does the full moon first start appearing? 6 p.m. What's happening to the sun at that point? It's setting. So the full moon rises as the sun sets. It has to. When does the new moon, and by the way, when does the full moon set? When the sun rises. When does the new moon rise and set? Same as the sun. Several people say that. It rises and sets with the sun because the new moon is in the same direction as the sun. So if the sun is setting, the new moon is setting. When does the waxing crescent set, roughly speaking? Yeah, around 9, 10, depends on how big it is, but a few hours after sunset. Yeah. When does the first quarter moon set? If it's overhead at 6 p.m., when do you think it sets? Midnight. There you go. Because at midnight, this direction is the direction of the first quarter moon, and that's the direction of the horizon. That is, the moon is setting. I love these kind of figure out type things. Do not go and memorize what I just said in the webcast, all the 4 examples or 5 examples I gave you, because I'm going to give you on the exam some other example that you haven't memorized. What you should understand and be able to reproduce is this diagram and think from this diagram what the implications would be at different times of the day and night and whether the crescent or gibbous moon is visible or not visible or whatever. You can't possibly memorize all possible combinations, and it's more fun to be able to figure things out, knowing a little bit. The thing you need to know and understand thoroughly is this diagram. From that, you can figure out everything else. And if you meet scientists, you'll find that there's a number of overriding themes. One is that they want to unify and understand many disparate phenomena using a small set of laws or relationships. Another is that they want to know the minimum amount of stuff and figure out as much as they can. Now, it helps to know a bunch of stuff too, but you gain more respect from your colleagues, not by knowing lots of stuff, but being able to figure out everything with a minimal amount of knowledge. because then it shows you're really, smart and stuff. And if you memorize stuff, okay, that means you're smart in some other ways, but it's different. And at least among scientists and mathematicians and people like that, you get a lot more respect if you can figure things out, not necessarily if you can memorize lots of stuff. So I like it when people figure things out, and I'm telling you that now. All right, good, I've done that. So what else did I want to say? One of the labs has you looking at the phases of the moon. Don't look them up on the internet or in the newspaper or anything like that. You should look yourself at the sky and not get any information from anywhere else. And you'll find some interesting relationships. Hopefully, you will see for yourself some of these things here that I'm talking about. Okay, cool. Let's move on to solar eclipses, one of my favorite topics in the universe because they are so magnificent. And scientifically useful too, but mostly they're magnificent and beautiful and just amazing. And take it from me, anyone who has seen one, real live, in person, at the place where it's happening, is a different person. It's a very moving event that changes you forever. And we all sound like lunatics to those who have not seen one. But once you've seen a total one, not partial, partial is fun, but got to see a total one, then you too become a lunatic. Let me just show you one here. Oops. Shoot. What happened? There it is. Okay. The moon is blocking the bright parts of the sun, allowing the faint, tenuous, very hot corona. We'll study the corona more when we describe the sun itself in more detail. But the corona is a hot, very low density, that is very tenuous region around the sun, which is normally completely washed out by the brightness of the sun's disk and scattering of that light by molecules in our atmosphere. But by an amazing coincidence, for which there is no clear physical reason that we can think of, the moon, though being about 390 times smaller than the sun in physical size, is also about 390 times closer to us than the sun is. And so their angular size, the amount of space they take up in the sky, the number of degrees, half a degree, that they take up in the sky, is almost exactly the same. So here's a little golf ball and a basketball. Actually, it's the official NBA basket small. You see, it's for little people. Anyway, it's bigger than the golf ball. I like to play with it, too. You get one of these little tiny hoops, and, it's bigger than the ping pong ball. But if I'm sorry, the golf ball. Sorry, don't know my sports. Tiger would be mad at me. Anyway, this golf ball is smaller than the basket small. But if I adjust the distance from my eyes such that the ratio of the distance of the sun to the distance of the moon, both from the earth, that is the ratio of the sun's distance from the earth to the moon's distance from the earth, that ratio, if that's exactly the same as the ratios of the sun's physical size to the moon's physical size, then they will look the same angle in the sky. If the moon's too far away, it looks too small to cover the sun. If it's too close, it covers the sun easily and more so. But to get the exact covering of the sun, I adjusted just like this. And you can probably even tell qualitatively or semi-quantitatively that the ratio of distances is roughly equal to the ratio of sizes. Can you see that? Okay. There's no clear reason for that. It's a coincidence. Of all the planets in the solar system, we are the only one that has a moon that precisely covers the sun. Jupiter gets eclipses, but its 4 big moons more than cover the sun. That is, the situation is a bit like this. They're a bit too close and big compared to where they should have been. And all the little moons just, they're like little fleas. They don't block much of the sun. So they subtend or, take up in the sky the same angle, half a degree. What do I mean by half a degree? Well, a full circle is 360 degrees. From horizon to horizon is 180 degrees. From the horizon to the zenith is 90. The moon and the sun are both about half a degree in angular size. So you could stack up 180 moons or suns end to end in going, say, from the horizon to the zenith. Okay? And it's just a marvelous coincidence. So basically, the moon casts a shadow on Earth. and only a very small part of the Earth has the sun fully blocked by the moon in this way. Other parts, like from here, looking at the moon, see it blocking part of the sun, but not other parts. See, this part of the sun we could see from here, say. And from other parts of the Earth, if this were drawn to scale, the moon wouldn't block any part of the sun. And that's what usually happens at new moon. And usually, at new moon, the moon doesn't block the sun precisely. Just one second. Because, though I lost my Earth, it's probably in my office somewhere. Earth is here. The moon's orbital plane around the Earth is not exactly coincident with the Earth's orbital plane around the sun. Rather, it's tilted by 5 degrees. So normally, when the moon is here, in roughly the same direction as the sun, it is a little bit below or above the line that would make them all collinear. Okay, it's not quite collinear because of this tilt. So there it's a little bit below where it should have been. But notice, a quarter of the year later, this orientation of the plane remains the same, but the thing is shifted over to here, and now the moon could block the sun, okay? So now there's the possibility of it blocking the sun. However, if it doesn't happen to be in this part of its orbit at the moment when it could be collinear, then it won't be collinear. Now I'll take that was a blue Earth here. I'll take it. Yeah, thanks. Shoot, I can't. There it goes. I'll take an orange Earth. Okay, Mars. Let's say. Well, it's not Mars, but anyway, if the moon is not in the right place at that moment, then it won't block the sun. So it is a necessary condition that you have this possible collinearity, which happens twice a year. By the way, it could happen over here too. But it is not necessarily the case that the moon will be at the right position at the moment when eclipse could, in principle, be geometrically possible. Same thing for total lunar eclipses. Here's the Earth, here's the moon. Usually, the Earth's shadow, and we'll talk about lunar eclipses at the rate I'm going, probably at the beginning of Monday, but that's okay. This is a fun lecture. Usually, the Earth's shadow doesn't fall on the full moon. But occasionally, it can fall on the moon. Let me show it over here because it'll probably be easier for you. So here I'm very careful to keep the orientation of this plane the same. So now it moves over to here, let's say. I think I just reversed the direction of motion around the sun, but who cares? Doesn't matter. Let it go this way. Okay, now I'm back over here. Okay? All right? You'll excuse me for that. And at this location, would there be a lunar eclipse? No, right? Because the moon's in the wrong place. But if it happened to be right there, then, well, you know what I mean. It's doing that because of the Earth's gravity, but, okay, you get the idea, right? The conditions for a lunar or solar eclipse are rarely met. And at most times of the year, it's impossible, and even during the times of the year when it is possible, it is relatively unlikely. So they are rare phenomena. And you were awfully lucky to see a total lunar eclipse at the beginning of this semester. So let me just show you some pictures just to, get you all excited. Oh, thank you for that Earth there. There's the unblocked sun, and here's the blocked sun. My first solar eclipse, total solar eclipse, was on February 26, 1979. I was a senior in college. I was at UC Santa Barbara, actually. And I flew up with my advisor to near the border of Oregon and Washington, in the Cascade Range there was the place where you might see the eclipse. And maybe the weather gods were saying, or the weather people were saying, that it might be clear, but they weren't giving us much hope because there was a big storm system across the Pacific Northwest. But here, in this overexposed shot, you can see the partially eclipsed sun, and then here it is. And there's still some clouds, by the way, so it was really cloudy early on. But then, as the eclipse continued, the clouds were clearing away, and at the moment that the moon just was finishing covering the sun, this last cloud cleared away, and it was just so totally glorious. And I just, oh man. Okay, I know I sound like a nut, right? But this is the way you become when you experience one of these things. The pictures, the words, even video, movies, and all that do not capture the emotion, the feeling, and the wide range of phenomena that are happening at a very rapid pace when this is happening. You know, the moon is eclipsing the sun, and, 10%, 20%, 30%, you kind of go yawn. The brightness of the sky isn't changing very much. But when you get to 90, 95, 98, 99, 99.9% of the sun is covered, right? It's all happening very quickly, and just people go crazy, animals go crazy, and I resolved to see lots of eclipses. Then for the next decade, I was busy. I was a student. I was poor. I was busy. I'm still poor and busy, but that's okay. Not as poor. But I didn't see many, and then I saw one in 1991, and from then on I'm totally addicted, and I've seen 8 of them. And I'm going to Mongolia this coming August to see one, and then in 2009 I'm going to Tahiti. So it's a rough life. Yeah. So So from only some locations do you see this totality. Okay, now, there was a question right there which I tabled for a second. Yes? What's your name? David says he's heard that the moon is actually moving away from us. Yes, it's moving away at roughly 4 centimeters per second, per year. Sorry, not per second. Boy, here today, gone tomorrow, So 4 centimeters per year. So you can calculate that in about 500 million years, total solar eclipses will be very rare, and in about 1 billion years or so, they will be impossible because the moon will look too small relative to the sun. And I'll talk later about why it's moving away. It has to do with the tides. So yes, David, that is absolutely correct. We are not only privileged to have this coincidence of shapes, of sizes, and distances, but there's a time coincidence as well. In the future, they won't be possible, and in the past, they were possible, but they more than covered the photosphere, the bright part of the sun, and so that also covered the inner corona and these little things called prominences that I'll show you in a bit, and other cool phenomena that are at the edge of the sun. So the eclipses weren't as perfect long ago, and they won't be possible far in the future. So we sort of live in a preferred time, give or take 500 million years, okay? So, which, right out of 10 billion, or out of, whatever, 10 billion years is roughly how long the sun will last. And, so we're in sort of a privileged time. Okay, now I mentioned that from many locations you'll see either no eclipse or only a partial eclipse. So from this location, for example, you'd be looking at the moon, and this is not to scale, but it'd be blocking this part of the sun, but it wouldn't be blocking that part of the sun. And the farther you are away from this path of totality, and I'll tell you in a minute why it's a path, not just a point, the way you might think here. It's a path because the moon is orbiting the Earth, so the moon's shadow falls on progressively, different parts of the Earth as the moon is orbiting the Earth. But anyway, the farther you are away from this path of totality, the less eclipsed the sun is. So here on July 11th, 1991, many of you were knee-high to a grasshopper at that time. In a few years, I'll be teaching this course, and no one will even have been born back then. But anyway, it's not fair. Professors keep getting older by a rate of 1 year per year, but the students don't. That's not fair, okay? The students remain the same age, and I don't get it. I've never figured it out, but all right. I'm just kidding you. Yeah, I have figured it out. But anyway, I like acting like a dork. Anyway, so the farther away you are from the path of totality, the less eclipsed the sun looks. So here's a cool little animation. Actually, not an animation. It was a series of photographs taken by a fellow in France, and it's sped up a little bit. This takes several hours, the partial eclipses. But anyway, you get different amounts eclipsed. And sometimes, if you're lucky, you get an eclipse under unusual circumstances, like at sunrise or sunset. So here you have these lobster claws coming out from the horizon, from the ocean, It's kind of cool, Imagine you wake up one day and you're a cave person or something like that. You don't know what's going on. You see these claws coming out of the horizon. It's like, yeah. Anyway. Well, people used to commit suicide and stuff because they didn't know why the sun was going away, and they thought the gods were angry at them. And in many cultures, they still beat pots and pans to drive the dragon away that's eating the sun. Now with science, we understand what's going on, and so you don't have to fear this phenomenon anymore. You can enjoy it. Anyway, partial eclipses are no big deal, but they're kind of fun. But to look at them, you should use special protection. You should not use regular sunglasses. They won't protect you. You should use Shade 14 welder's glass. You can get it at welding supply shops. And I got a bunch of them here for like, I don't know, $1.89 each. So I'll give them to you for $2, basically at cost, and that will save you from having to go to a welder's store if you want one of these things. And they're useful for just looking at the sun even when the sun isn't being eclipsed. Like you can look for sunspots and stuff. We'll study sunspots later, but you can find some. Some are big enough to see with the naked eye if you occasionally look at the sun. And so for $2, it's a useful thing to have. And I only make 11 cents on it, which probably pays for the gas, you know, when I drove to the welder's store. But anyway, this is a good thing to have. And I've been to eclipses all over the place. This is one in 1995 in Thailand. And here are a bunch of monks using these glasses, you know, using these Shade 14 things, or Mylar. They might be using Mylar, which is pretty good too. And here in Peru in 1994, this lady has had some really good stuff or something. But anyway, she's enjoying the sun. She's enjoying the sun. She's getting high from the sun, the spectacle of the sun. This is the greatest high you can get. Don't go for all these, you know, fake substances and stuff. Watch a total solar eclipse. It's much better. So anyway, this is useful. And you don't have to buy it, but if you wish to buy one of these, I have a supply, and you can come up after class, give me $2, and I'll give you that, okay? One year I had like a whole pile of money. Someone took a picture and it looked like I was dealing drugs or something. But anyway, you know, so, and I'll have them next week as well. Oh, this is also useful if you're doing lab number 2, the setting sun lab. You don't have to do lab number 2, but if you're doing lab number 2, it is useful to look at the setting sun through one of these filters. It's especially important to have a filter when you're projecting the sun's light through a telescope, because what does the lens or the mirror of a telescope do first and foremost? Collects light. Yes, I hear in unison, collects lots of light. So if you're taking all that light and you're focusing it in on your eyeball, not good. I mean, how many of you make a practice out of staring at the sun even without binoculars or a telescope? It hurts, okay? So if you're collecting a lot more light, like telescopes are prone to do, that's why they're built, you're going to, you know, put even more light and heat in your eye. So you do not want to be looking through the eyepiece, but you can project the sun this way. Here are my kids. They hate this photograph because it's many years old, but this is Simon, that's Zoe. And they're projecting the sun. It's a bit hard to see there, huh? Well, yeah, it's there. Through a little telescope that I got when I was a freshman in high school. So I discovered Saturn through that telescope. I'll tell you that story later on. That's what got me going. Anyway, you can project the sun's light through a telescope, but if you were to look through the eyepiece without protection, this is what might happen. This is the lens cover of one of these little telescopes, like this one or that one. And it didn't, you know, the telescope didn't have a filter, and the lens cover was placed on the telescope. Actually, one of my GSIs did this years ago with a telescope we had on the roof of Campbell Hall. I'm lucky it was the lens cap and not his eye that was at the focal point, okay? Because look what happened to the plastic lens cap. This is serious business. Do not look at the partially eclipsed or uneclipsed sun without adequate protection, okay? The totally eclipsed sun, the bright parts are blocked off, and there's just the faint, tenuous corona. Perfectly safe to look at that, but not the partial phases. You need some sort of protection. And if you don't have a telescope, you can make a simple pinhole camera by not having any glass or lenses at all. You just take a piece of cardboard or paper or wood or whatever, punch a hole through it. If you have a luminous object like this arrow here, you can trace what the rays of light are doing. This one from this end goes through the hole like that and makes an image on a viewing screen down here. This one there makes an image up there, and everywhere in between, it's, you know, they fall in their respective places. So you get an image, a projection of a luminous object by using a pinhole camera. And this is the simplest kind of camera. You could put a photographic emulsion here and get a photograph even without any lens or anything else. Cameras are much better nowadays. But anyway, notice it's inverted. When you're looking at the sun, who cares? You know, crescent looks that way or that way, who cares? Anyway, so here I'm showing, at an eclipse in 2005, one of these pieces of cardboards where I've cleverly punched the holes to spell my son's name. And there was a close-up of the projection, and it says Simon, and you can see all these little crescent suns, partially eclipsed suns, and you got to eat celestially themed candy and gum during momentous events like eclipses. You got to do it, right? Because otherwise you're just like, you're nobody, right? So, or orbit gum. Orbit would be the next most appropriate thing to eat during an eclipse. There are other times you might want to eat celestially themed candy, like when you're looking at Mars through a telescope, you might use eat a Mars bar, or where you're looking at the Milky Way through your binoculars, you might want to eat a Milky Way bar. All right, well anyway, there's a bunch of images. I know, this is really bad, but I degenerate quite a lot during this lecture every year because I just love eclipses, and these are just the partial phases. So the excitement is all building up and stuff, but wait till you get to totality. Man, oh man, it's like, whoa. Anyway, so what's next here? Oops, I have the wheel of death. Wait, oops, I didn't mean, no. So even holes in leaves, the natural holes that you get in a tree between the leaves, can produce little images like this. And the images are round, not because the holes in the leaves and the spaces between the leaves are round. They're arbitrary shapes. The images are basically round, except for a bite being taken out, because the sun is round. So here, these things look basically round, but crescent-shaped, not because I made round holes in my cardboard, but because the sun is round, okay? And in a similar way here, it doesn't really matter exactly what shape your hole is. You will still basically get a round image, and the wider the hole, the brighter your image will be, but also the more fuzzy it'll be. You get a sharper image with a narrow hole. And those photographers among you understand that it's the same thing with cameras. With a high f-stop number, you can tend to get a sharper image, actually, in some cases. Doesn't matter why, but anyway, don't worry about that. But anyway, I just thought this was really cool. This was at the Mexico 1991 eclipse. I just happened to be wandering around, waiting for totality, and I was under a tree, and here are all these cool little crescent suns. Okay, well, while waiting for totality, you have to amuse yourself. So my wife thought of this kind of a thing, little Pac-Man thing, that, it's sort of, it's, let's give him an eye, so, yeah, I know. The partial phases take an hour or so. Totality lasts anywhere from a few seconds up to a few minutes. 7 minutes, 7.5 minutes theoretical maximum. So you better not be snoozing. You snooze, you lose during totality. You snooze during the partial phases, it's no big deal. But you shouldn't snooze because, whatever. So anyway, it's kind of fun. You can do lots of things. You can take like a monocular. I forgot my binoculars, but take a monocular or a little telescope and project the sun, kind of like in those photographs I showed, and project it on the shadow of a person. And there, of course, is the eclipse gum, right? Got to have the eclipse gun. Well, this is with a single telescope. What is a pair of binoculars? Forgot mine from home, but it's two little telescopes glued together. Kind of weird. A pair of binoculars. Well, does that mean you have two binoculars? The binocular is already a pair. Anyway, this is one of these things like, why is it first quarter moon and full moon when in fact that logically doesn't make sense? But anyway, if you do it with a pair of binoculars, then you can get kind of an interesting thing. Here you can kind of see these, we call these C cups, and So reverse C, yes. Oh, you can be creative, Anyway. All right, so what's going on? You don't get just one spot on Earth where this happens. You get a path because the moon, during this process, is actually orbiting the Earth. And so, the projection of the shadow onto the Earth's surface changes. So like when the moon was there, the shadow was projected onto that part of the Earth. When the moon's here, it's projected there. And when's the moon there, it'll be projected somewhere here. So in fact, here's a time-lapse photography of I guess 7 or 8 instants during an eclipse, the July 11th, 1991 eclipse. And this is, 7 or 8 snapshots of where the moon's shadow was on Earth as a function of time. And it takes a couple of hours for the whole thing to go across the Earth. So anyway, and it's kind of fun. But anyway, so here it is. Here's the stages, and now I'm going to get into totality. Enough of all these partial phases. Let's get to the real thing, So here's the partial phases, and now you're starting to see some really cool stuff. Okay, first of all, it's getting dark. And right about now, it's just about safe to take off your protective glasses and look at the sun. When a tiny, tiny, tiny sliver of it is left, you can look at it. And you start seeing the prominences, little hot plumes of gas, like little tongues of gas coming out of the sun. And then this is called the diamond ring effect. The inner corona is becoming visible because only a tiny fraction of the sun's photosphere or bright parts are visible, and they're highly overexposed, which gives you this effect here. Actually, the sun is only sticking out a little bit right here, but it's overexposed here, but so it looks like a diamond, and you get this ring. So this is called the diamond ring effect, and you get one at the beginning of totality and at the end of totality. So this is the diamond ring effect. Here's totality, and this is the inner corona. Here's some of these prominences. We'll talk about them more when we study the sun as a physical object. And then closing in on one of the prominences, they're all loopy like this, and that's because they're ionized gases following the magnetic field lines that are inside the sun and surround the sun. So this is really, I like this photograph. And then a longer exposure reveals the outer parts of the corona. But you see much more than any photograph that I've ever seen can show. Some photographs are doctored to make it look like what you're seeing. But your eye has what's called a very wide dynamic range. It can see faint things and bright things in the same picture, in the same view, whereas photographs generally are tuned either to the bright stuff or the faint stuff, and the other stuff is either underexposed or overexposed. So your eye sees much more, and it's a dynamic phenomenon. It's not just you come outside and there's the eclipsed sun. The whole thing is changing, and the excitement level is out of this world. Again, you can and should look at a total solar eclipse with an unaided eye, binoculars, or a telescope. This phase is totally safe because only a small percentage of the sun's total light is being scattered or emitted by the gases in the tenuous corona. So that's perfectly safe, but the uneclipsed parts are not safe. Okay, so what else do I have here? Here's another diamond ring at the end of the totality, okay? And here, clever photographers can do these multiple exposures, with, beautiful foregrounds and stuff. A church in Mexico in that particular case. Here's a video of an eclipse in Australia that lasted only about 20 seconds, but it was taken by my co-author, Jay Pasakoff. This happened during the last week of classes a few years ago, and I love my classes, and I just could not leave the last week because everyone's all stressed out the last week. And plus, I thought they might have cloudy skies, but they didn't. I mean, it was a close call. Look at all these clouds. This is sped up a little bit, I think, but it only lasted, I think, 25 seconds. So this was perhaps sped up by a factor of 10. But they were lucky that one of these, babies wasn't right there at the time that the sun was being eclipsed. And I got out here. This has audio. Okay.
Data at 125.
Peru, 1994.
Alpha.
Can you hear it? Can you hear the microphone?
Beta.
Yeah.
Alpha. 60. 30. One ring. 125. Yes! Son of a gun! Whoa! Wonderful. Wide angle. Oh, this video is cool.
Oops. Earthquake.
Video is cool. Pull the video back a little bit. Man, we're doing it again! Yes!
This is not me.
Beta.
Not much time passes.
Beautiful. Chromosphere. Speed! Alpha at 125, beta at 30th, alpha at 125, beta at a 30th, alpha at...
Yeah, that's pretty good. Here's my T-shirt. The beads they were talking about. Yeah, I'm an eclipse chaser, right? So the beads they were talking about. If I could just go back, let's see if I hope I don't mess things up. The chromosphere that one of the people mentioned is a very thin layer of the sun just outside the main part, the photosphere. Then here are prominences. And then the beads they were talking about, what? Oh, no screen. Oh, that's very bad. Why is there no screen? That would be bad. Did we have the video show? You saw the, oh, okay, great, okay, cool. The beads they were talking about, that's a bead. That's called a Baily's bead. It's a little bit of sunlight shining through a valley among mountains on the edge of the moon. So the moon's surface is not perfectly smooth like a billiard ball. There are mountains and valleys. So here, with the moon nearly fully covering the sun, there was a little channel, a little shaft through which sunlight still shined, and that's called a Baily's bead. The last Baily's bead, in a sense, can be thought of as the diamond ring, but all right, let me move forward here because I have a bunch of other stuff. I think I can just zip through here. Come on, there it goes. Okay. Oh, and you get these twilight sky colors all around you because the path is very thin, maybe 100 miles wide or so, or 50 miles wide. So if you're looking off in some direction, you're seeing an area where they are seeing like a 99% eclipsed sun. So they're seeing a very diminished amount of light, and that light is going through 50 miles of atmosphere to you, and so it's getting scattered and absorbed, and so you get the twilight sky effects as though the sun were setting, but you get it in 360-degree horizon around you, not just toward the west. So, yeah. And, animals go crazy. Elephants go stampeding around. This was a doctored shot, but yeah. So anyway, here's a bunch of eclipse paths. And I want to tell you a story. In 2005, April 8th, there was an eclipse right out here. Again, remarkably close to Tahiti, but we were on a cruise ship, my girlfriend and I, and we went to Pitcairn Island. It might be that little thing right there. Or that might be Easter Island. But anyway, one of these little dots. And so Pitcairn Island's really great. It's where the mutiny on the Bounty occurred. Well, I mean, the mutiny occurred earlier, and then the people settled on this little rock in the middle of nowhere that wasn't on any maps and stuff. So it was a cool place to visit. How many people do you know that have been to Pitcairn Island in the middle of the South Pacific here, not near anywhere, So anyway, we went there, and it was really great. It was a lot of fun. So here it is, Pitcairn Island, HMS Bounty, last resting place of the HMS Bounty, And, we took an ATV ride on the island. It's pretty small and stuff, and saw some amazing sights and stuff. But anyway, the eclipse was April 8th, and that day started out pretty well, clear morning skies, a bit of clouds and stuff, but here I am, and we were happy, we were kind of happy at that point in time. And then it started clouding over, and more clouds as the eclipse was progressing, the partial phases, and we were not pleased. And I was kind of going crazy, and I resorted to praying, and then just as totality was beginning, the last cloud cleared away. And totality only lasted 30 seconds. This was a very short eclipse. And it was just amazing. Look at that. And here's this giant cloud, and totality just started and lasted 30 seconds, and we saw the whole thing. But boy, was the adrenaline going, okay? I mean, it was really going. I mean, it was, yeah. This adds to the excitement. So anyway, here's a fisheye shot of all the people on the cruise ship and this totally eclipsed sun. This is a few seconds later. The cloud moved away. They were really humming along. So then we were really, very, very happy and stuff. And it was a beautiful eclipse. There's some pictures of the eclipse. There's the chromosphere, this colorful part, and the prominences. You don't get to see that not during an eclipse, And everyone's having Mai Tais and stuff, and, it's great. And we were just, having a lot of fun, really a lot of fun. Great fun. And it even started to rain a short time later. There's the raindrops. But we were still smiling because who cares about the partial phases after you've seen totality? You don't care anymore. Well, that eclipse was extra special for me because I proposed to my girlfriend, Noelle, at the time. And we actually wanted to get married on the ship, but it turned out it wasn't legal. So, but yeah. Yeah, you couldn't do it, not in those waters, or I don't know what the rules were, but I proposed, and I didn't really give her a super fancy ring, but you could say I gave her not one, but 2 diamond rings. One diamond ring at the beginning of totality when the cloud was just clearing away, and another diamond ring at the end of totality. So she got 2 diamond rings, not one, and so we're thinking of making a T-shirt that said, I got engaged at the South Pacific total solar eclipse, and all I got was this diamond ring. Well, it gets better. I have 2 minutes left, and I want to just complete this story, because that was April 8th, 2005. The next eclipse was going to be March 29th, 2006. going through Turkey, Egypt, and Libya. And I go with these travel agencies. They hire me to teach people how to correctly and safely view an eclipse and tell them about astronomy and all that. And they don't pay me, but on the other hand, I don't have to pay to go on the trip. So it's a really cool deal. I get to go all over the world. So I was going to go to Egypt on March 29th, 2006. But, we were going to have a baby and everything. And that was the 1 month we were trying to avoid. But somehow we screwed up or something. And that was the 1 month we didn't avoid. And remarkably, the due date, the nominal due date of the baby girl was March 29th, 2006. Can you believe that? I mean, yeah, it was like, oh man. So I canceled, I mean, is this cosmic or what? I mean, that's more cosmic than the existence of eclipses, themselves, physically. Well, a bunch of friends of mine sent me photographs because I canceled my trip. I wanted to be there for the birth of my daughter, and, I would have been in the doghouse had I not been there. But that's a lesser consideration. I think Noelle's watching this lecture because I told her today would be about eclipses. Anyway, hi there. I wouldn't have gone, okay? Even if I weren't in the doghouse. But I was told by people that the corona was spectacular on that eclipse. And it was. Here's one of these doctored photos that shows you more of what the eye would have seen. So in honor of the fact that we got engaged at an eclipse, and also that my daughter was supposed to be born on the eclipse date, she was actually a few days late, April 2nd, but that's okay, that's 42, 42, one of the best numbers in the universe. In honor of the corona of the sun, not the beer, her middle name, one of her middle names is Corona, okay? That's shortly after birth. And then the Nicole comes from the fact that half the people that meet my wife call her Nicole instead of Noelle, and so we just thought it'd be funny. So, our baby is going to grow up, and she won't realize until later that her name is a big joke. But it's a very personal, loving joke with much history and stories behind it, okay? So that's that. As I said, I've been to a bunch of them, 8 out of 8, would have been 9 out of 9, but hey, Capri was worth it. Next year, I'll be in Mongolia, August 1st, 2008, just before classes start. It's great to be able to travel now to all these distant places because I get to see the world and my way gets paid. This trip is going to be remote, hard to get to. July 21st, 2009, there's one that crosses over parts of China. It's this one here. It starts in India, goes over China, and over the South Pacific. I'll be once again on a cruise ship near the end of the path there. But on the 21st of August, 2017, there will be one crossing from the Pacific Northwest down to, looks like North or South Carolina, perhaps. You have got to be there, okay? If I find out that you were 200 miles away and didn't go to the path of totality thinking that, oh, I'll see 97% of what there is to see, you're not seeing 97% of what there is to see. You gotta be in the path of totality. And if I find out you didn't go 10 years from now, you will retroactively fail this class, okay? So you gotta go. And then remarkably, 7 years later, April 8th, there's another one that goes across the U.S. and happens to cross in southern Indiana or Ohio or something like that right there. So we will have 2 in quick succession after waiting from 1979. In general, you have to go to where the eclipse is. It won't come to where you are. From a given place on Earth, on average, you have to wait 360 or 380 years for one to randomly come to where you are. Okay, have a great weekend and go Bears. Yeah, thank you. We'll finish off on Monday.